Welcome, data managers. This is Mr. Dunbar, and I am now going to go over Learning Activity 6.3 Theoretical Probability. This is part of the Solving Probability Problems unit. So you'll recognize the formula for theoretical probability. The probability of event A happening equals n of A divided by n of S. So let's take a closer look at what those are. So n of A is the number of times that an event will occur, and n bracket S bracket is the number of total events in a sample space. So n of A is a subset, n of S is the whole kit and caboodle. Now let's try something. Let's calculate the theoretical probability of rolling doubles when you're rolling two six-sided dice. So your first dice, the outcomes are listed here at the top, 1 through 6 in red, and your second dice, the outcomes are listed on the side, 1 through 6 in blue. And each number in the table is going to represent the sum of two dice. Now, what this table shows us is that there are 36 outcomes when we roll two dice. Now, let's find the double events in that particular table, and we find that there are 6 doubles every time you have an intersection of the same number, so 1, 1, 2, 2, and so on. Now, we can calculate probability using this. So you'll recall the formula that we just looked at and that we looked at in a previous video. So in this case, let's define event A as being the event when we roll doubles. So probability of event A equals 6 possible events where we roll a double divided by the total number of the sample space, and you'll remember that there were 36 possibilities. So in the end, 6 over 36 reduces to 1 over 6, 1/6. Now let's take a look at the examples. So here we have a number of examples. The first one asks us to find the probability of rolling an 8 when we are looking at two separate dice. And if we look at that table that we generated, you'll notice that we have an 1 8, a second 8, a third 8, a fourth 8, and a fifth 8. So that means there are 5 possible combinations where we get 8 as our sum. So in that case, the probability of 8 is 5/36. And I'm going to leave it up to you to work your way through the remaining examples. They're fairly straightforward. Although, do you know what? Let's take a quick look at the complementary one. This is going to force us to think about the complement again. So let's take a look at question 4. Find the probability of not rolling doubles. So you can approach this two ways. You can take a look at the number of outcomes where you do not roll doubles, and we'll notice that there are 30 out of 36 possibilities. Or we can take a look at the complement. So we've already established that the probability of rolling two dice the same is 1 in 6. So the probability of not rolling two dice the same is going to be 1 minus 1 over 6, which is 5/6, and that is what 30 out of 36 reduces to. We can also use tree diagrams to get at theoretical probability. So we're going to try to figure out what is the probability of tossing heads twice if we're going to toss a dice 3 times. So in this case, we're going to list all possible outcomes using the tree diagram. And you'll notice our first toss is here at the top, either heads or tails, and then each head or tails is subjected to the second toss, another head or tail, and then each of those again is subjected at the third level to another toss, head or tail. Now, what we care about in this case are the branches. So we've got a branch going from head to head to head, we've got a branch going from head to tail, and so on. We list all of those possible outcomes, and we end up with a sample space with 8 different branches in the tree. And they are listed here. The events where heads were tossed twice are highlighted in blue, which means that the probability of tossing heads twice in 3 flips is 3 in 8, or 37.5%. Notice how we excluded HHH, and that's because in that case we rolled heads 3 times. Now, if we'd expanded our question to include the phrasing, what's the probability of tossing heads at least twice in 3 flips, then we would include HHH, and then our probability would have been 50%. So let's take a look at 2 other examples, and you'll notice that the first example goes right to the at least phrasing. Find the probability of tossing at least 1 head in 3 tosses. So the probability of tossing at least 1 head in 3 tosses is the probability of tossing no heads in 3 tosses. So the probability of no heads is 1/8. So 1 minus 1/8 is 7/8. So the probability of tossing at least 1 head is 7/8. Let's take a look at our sample space, and we'll see that is confirmed. So the probability of tossing no heads only occurs once, and that's when we've got 3 tails. So that's 1/8. And let's take a look at this other question here. Find the probability of tossing heads at least once if the coin is tossed 5 times. So we're tossing heads still at least once, except this time we're tossing the coin 5 times. When we're tossing a coin 5 times, you have 2 to the power of 5 possibilities, so that's 32 possibilities in the end. But in this case, we still have only 1 event where no heads show up at all. That's where we have all tails showing up. So it's 1 minus the probability of no heads. 1 minus 1 over 32 is 31 over 32. We can also use the fundamental counting principles and the permutations and combinations to get at theoretical probability. Remember that permutations have an order that is important, while combinations do not have an order that is important. They don't care about order. So in this example, we're going to have a family that lines up for a photograph. We've got 3 children. They're going to be randomly placed in a row. So what is the probability that they will be lined up in ascending order of age? So the first question to ask is, how many ways can you line up 3 children? So in this case, the number of ways, which is going to be our whole sample space, is going to be 3 factorial, because we have 3 children, 3 different ways of lining, or 3 factorial ways of lining them up. 3 permute 3 is 6. So now, how many ways are they in the correct order, in ascending order? And this is going to be your n of a, so the number of events, not the total number of sample space. And in this case, there is only 1 right way to do things. So n bracket a bracket is equal to 1. So in this case, the probability of lining up according to age is 1/6. 1 being the number of events that we care about, 6 being the total number of ways to line up. Our fourth example has a basketball team with 9 players. 5 of them can be on the court at any time. So what is the probability that both the captain and the assistant captain start the game? So in this case, A is going to be the event of both the captains starting the game. And in this case, how many lineups can we choose? Well, we have 9 lineups, or 9 players, and we choose 5 of them. So that's 9 choose 5. Our answer is 126. That is our sample space, our total number of options. Now, how many lineups will contain both of the captains? So, in this case, we are, again, choosing players. So, for the captains, we've got 2 choose 2. That they act as a cluster, so both captains have to be on. So that means we are left then with 7 players from which to choose, and we have only 3 remaining spots to choose. So we've got the 2 choose 2s, 2 choose 2, which is 1, and we are multiplying it by 7 choose 3. In the end, we get 35. So the probability of having both the captain and the assistant captain start the game would be 35 divided by the total sample space, which is 126. So 35 divided by 126 is approximately equal to 28%, or 0.28. we're about to hit the 10-minute mark, so I am going to leave it up to you to go back to the content and finish these questions and take a look at the examples that are here.